again, and we're going to try to solve another problem from chapter 1, but now about related rates. So related rate problems are usually pretty interesting for physics majors because they're pretty familiar. For calculus students, it's one of the not so memorable experiences, but it should be very appropriate for this class. Now, generally, for a related rates problem, you would has something to do with the geometry or some sort of formula that changes with time. It has to be a function of time. That's what you have to look out for. And once you have a function of time, then you will have to differentiate or use your derivative techniques to find what's changing, and usually it's within a snapshot of time as well, as we'll see in this problem. Okay, so let's break it down. So what are we given in this formula? So we're given a few things. That it's a sphere, even though it's a simple, we'll need that, and that the volume decreases. So there's a volume decreases at a rate, and so that means it's negative. So it's important to know that it's negative, otherwise a simple minus sign can change your entire answer. And our snapshot in time is finding out the radius, the rate of change of the radius when it is exactly, when the diameter rather, not the radius, is 0.10 meters or 10 centimeters. And we're trying to show, in this case, that the radius, dr, well, if the volume is decreasing, then this also has to be decreasing as well by that much. And notice this centimeter does not have anything squared because it's just one degree of freedom right there. And formula, this one is actually not too bad because the only formula we need here is the volume of a sphere, which is 4/3 pi r cubed. Okay, and so pretty much we're already ready to solve the problem. And so we need to take the formula for the volume, which is our first clue, but then we differentiate both sides with respect to time, because our given is actually with respect, and our goal is with respect to time. And so make sure you follow all the rules for differentiation. dv dt, 4/3 pi is constant, so you can take that out, or the derivative of that is just 0. And then the 3 comes down. You have r squared, but don't forget to take the derivative itself of dr dt. Okay, as you can see here, that cancels out. Okay, and pretty much we're already given everything else. We already know what the change in volume is. We know what the radius is. We just have to divide the diameter by 2. We don't have to worry about the 4 pi, and this is what we're looking for. So we're actually good to go. Okay, I'm just going to switch things around a bit. Okay, so I'm going to multiply both sides. I like to get the final formula. So what we're looking at is I just switched it around. Okay, this side went over here and that side went over there, multiplying both sides by 1/4 pi r squared, so that would cancel out and go to the other side. And then from here, it's just plug and play. This would end up being 10 cm divided by 2, and this would be negative 2.0 cm cubed per minute. Now notice on the bottom this is going to become 1 over 4 pi 25 cm squared times negative, just to show out the units. So this cm squared get canceled, and we're only left with the units of what exactly what we're looking for, cm per minute squared. And from there, it's just pretty much a matter of plugging into your calculator, and you should get this order of magnitude 3, negative 3. That is, okay? And so make sure that your units follow along to what you're looking for, radius per second or per minute, unit time, and that it also is decreasing. And if the volume is increasing by 2.0, then the radius is not increasing by that much, okay? Because it's a snowball, something probably hand-sized, okay? And that is it. Enjoy.